Hello everyone, welcome back to Risha Education. So we have been doing videos for Joseph A. Gallian 9th edition question series. Now we are doing chapter 2 for that, and we have already solved 25 questions in the past 5 videos. You can go and check that out. And now we are doing 26th video in this 6th video, a 26 question in the 6th video. So we'll be doing up to question number 30th. That means 5 questions in one video we are aiming. So let's see how much we are able to do now. So let's get started. So this question says that prove that in a group we have A inverse whole inverse is equals to A. Okay. So we know that for any element A, there exists an element B such that AB is equals to identity for a group, for inverse to exist. So if this happens, we say that B inverse is equals to A, or we can even say that A inverse is equals to B. Now what happens is if we replace B by A inverse, what we get is A inverse whole inverse is equals to A. How we did this? Because we know that A into A inverse is equals to identity. Now this inverse is this, so we can write it as A inverse whole inverse is equals to A. I hope this is clear. This is very, very simple and this is very easy as well. I hope you like this. And let's move on to the question number 27. So we have for any elements A and B from a group and an integer n, prove that A inverse B to the power n is equals to A inverse B to the power na. So in my previous video, I have already said that whenever we see these type of question, what we apply is our 11th concept, that is principle of mathematical induction. So we will show this for n is equals to 1. Then LH, first of all, we define our statement. So what is the statement is basically A inverse BA to the power n is equals to A inverse B to the power n A. Now for n, this principle of mathematical induction works for the natural number. What about integer? Because we are working in a group, so that is why anything n with the negative power, it will become minus n, and some x to the power minus n will become x inverse to the power n. And if x is in the group, then x inverse must be in the group, and we represent x inverse with some element y, and we write y to the power n, and this becomes again a positive integer, and now we are able to use the formula. So this is how the whole integer works with the principle of mathematical induction in our group. So we will do this. So for LHS, we have n equals to 1 is A inverse BA, and for RHS, we have A inverse B to the power 1A, which is equals to A inverse BA. So hence LHS and RHS is equal. So we can say that P1 is true. Now consider PK be true. So we are considering this, let PK be true, and we want to show it for K plus 1. Why we want this? Because if P1 is true, then from K plus 1 we can say P2 is true, and then from K plus 1 we can say P3 is true, and so on we can do that. Similarly for the negative one as well. So PK be true will give you A inverse BA whole to the power K is equals to A inverse B to the power K A. Now we will consider PK plus 1. So for LHS we are going and we will show to RHS. So it will be A inverse BA to the power K plus 1. This gives you A inverse BA to the power K and A inverse BA. Now what happens is A inverse, because K is true, so we can write this as this, and we have A inverse BA. So by the associativity of the group, we have this, and we will go even forward. Then we will arrive at BA, which is equals to A inverse B to the power K plus 1 into A, which is our RHS basically. So hence This is true, and this is true for every n belonging to the integer. Okay. So next move on to the question number 28. So this also we can do by induction. Induction on Sawtooth property, because for two elements, what we know is A1, A2 inverse is equals to A2 inverse and A1 inverse. So we'll consider for K, I'm doing it very brief way because I want you to do. So we are considering it true. Let it be true. So we are considering it as true. So what happens is AK inverse, AK minus 1 inverse, and A2 inverse and A1 inverse. Now, we want to show it for K plus 1. So we have A1, A2, AK, and AK plus 1 whole inverse. What I will do bracketing method. I will use bracketing method. So till AK, I will consider it as one element, say A. And now I will consider one other element as B. So I have shown for two elements already. So what I will do, I will use AK plus 1 inverse and then A1 to AK inverse. Then this will give me AK plus 1 inverse and AK inverse and up to A1 inverse. So this is what we actually required. So from here we can say that this is true for all. And what we required is A1, A2 to AN inverse. From here we can write it as AN inverse, AN minus 1 inverse, and A1 inverse. So for 2 we say it as Sawtooth property, for 3 we say Sawtooth boot property, but for N we don't have exact name. But yeah, this is how the property works. Next, move on to the question number 29. So 29 is very similar to one of the previous questions that we have already solved. And the question says that the integer 5 and 15 are among a collection of 12 integers. So which forms a group under multiplication modulo 56. So we have S, the collection of 12 elements, which forms group under multiplication modulo 56. Okay, this is a group under multiplication modulo 56. We want to list all the 12 elements. So you know how to, when we say that we want to list all the elements, the first property that comes to our mind is closure. And the second property that is even important is the identity. So using this, we will try to find all the 12 elements. So what I did, if I know that 5 is there, then 5 times 5 must be there, then 5 times 5 times 5 must be there, or any multiple of 5 must be there. So I started doing that first. So first of all, I did 5 is equals, let me change the color. Yeah. So what happens? We have 5 and the 5 is available here. Now, when I did 5 square, it gives 25. So it gives 25 and 25 modulo 56 is again 25. So I am filling here 25. In this way, I will try to fill every numbers. Again, I did 5 cube and 5 cube is 125 and which gives 13 as the remainder. So the next number is 13. Similarly, when I did 5 to the power 4, it gives 9. When I did 5 to the power 5, it gives 45. And when I did 5 to the power 6, it actually gives us the identity element that is very important. So we have identity element as 1. Because we know in multiplication modulo, we have 1 as the identity element. Now, if further when I will multiply 5 to the power 7, it will give you 5 only. So that is why now we will not further multiply the elements because they will just repeat in this cyclic order. So now what happens, I will move further to see what else be the combinations for the closure to be satisfied. So then I saw another element which was given to me is 15. So I did 15 modulo 15 only, but when I did 15 square, it gave me 1. So when I have already written, so I cannot write it twice in a set. So that is why I move further and try to multiply these two because anyone can multiply these two and see whether the closure is satisfied or not. So I arrived at something called 75, which was congruent to 19 mod 56. So I write it as 19. Again, I multiplied 19 by 5. You can do any combinations. I'm just giving you one combination. You can try it by yourself to get more and more visual concepts for this. So 19 times 5 gives you 95, which is 39. Now again, 39 times 5 gives you 27. And 27 times 5 gives you 23. 23 times 5 gives you 3. And here we came to the end of all the 12 integers that were required for us. In this way, you can find, or in any other way which is suitable for you, you can find it. I have done for 5. You can just for multiply 5 into 15, which gives you basically 19. And you can do 19, 19 square, 19 cube, anything you can do using all the given concepts and given or basically all the properties and combinations you can apply. The only thing you need to keep is the identity. So here the 30th question we arrive at, and this is that we want an example of a group with 105 elements. So in the theory part also you have read that if we want any group of order n, in irrespective of whether it is abelian or non-abelian, the first choice that should come to our mind is of course Zn with addition modulo n. For every n, this forms a group. We have read in our theory part. If you have not read, you can simply prove by proving the 4 simple things required for proving a group. Okay, so this forms a group. So we are asked to find one group of order 105. So you can simply write Z105 is the answer. Now, secondly, the question is getting smarter. Why the question is getting smarter? Because we are asked to find 2 examples. So 2 examples with 44 elements. So now how we can find 2 examples for 44 elements? Because one is very simple, that is Z44. And the second, which you have studied in chapter 1, that is symmetry group, which is basically D2N. Or sorry, it's Dn, which have elements 12. So basically it will be D22 because it will contain 44 elements. So one another group which I will like to just share with you is Z11 cross Z2 cross Z2. So this you will learn when you will learn cyclic groups. What is the difference between this and this? So basically, this is not a cyclic group. Don't worry about that you don't know cyclic group. In further videos, you will definitely learn about the cyclic group and many other types of groups. So this is not a cyclic group, but this is a cyclic group. This is cyclic and abelian. This is not cyclic, but abelian. And this is neither cyclic nor abelian. So for anyone who knows this, it's very good. If you don't know this, in the further video, you will learn this. So don't worry about that. I hope you like the video. If you like the video, please subscribe to the channel and share it with your friends and like it. It will cost you nothing. Just help us to grow more. And thanks for watching.